Thanks, Ravindra. So, welcome, folks. Today, we are going to talk about another use case of in-band telemetry, which is about identifying network performance anomalies. Um, Today we have Ding Ma from Alibaba, who will be co-presenting with me about IFA deployment use case at Alibaba. And I am Bhaskar Chinni, I'm product manager at Broadcom. I will give you IFA introduction and the use cases, and then Ding Ma will deep dive into the specific use case of network performance anomaly detection. We will call it NPA as a shortcut. So some of you may have joined the previous session. Sorry for the repetition. Broadcom is innovating from silicon to silicon. No big surprises there, but for us, telemetry is a key focus area. And a lot of features have been added in the recent silicon, in-band telemetry, flow tracker, mirror on drop, many other features. Queue congestion monitor is also another one that was presented earlier. And all these features we support in our silicon and also contribute through size specification for wider community adaptation. So Sai is a sub-project of OCP, as you all know, and TAM v2, telemetry and monitoring TAM specification, is specifically focused on telemetry features. And Broadcom has contributed all these features. I'm just recapping them here. So let's dive into IFA. So what is IFA? IFA is in-band telemetry implementation of Broadcom. And what is in-band telemetry? It's about capturing packet processing metadata as part of user packet itself, instead of updating some counters that can be retrieved by the network operating system or a remote collector later. So as the packet traverses from one hop to another hop, each hop adds its own metadata to the packet in the data plane. So no control plane involved, and that means it is a highly scalable solution that is providing packet level granularity. And this is enabling several use cases. We will discuss those. And the idea here is, you are familiar with probably ER-span and other technologies where each hop is sending a copy of the packet and some metrics with it. The problem with that is if a packet is traversing 5 hops, you get 5 reports. If a packet is traversing 10 hops, you get 10 reports. That means collector has to deal with a lot of load and synthesize that data and gather analysis or analytics. With in-band telemetry, each hop is adding its metadata, but only the last node, the egress node, will send a report to the collector. And that means no matter how many hops the packet traversed through, the collector will receive only one report with per hop metadata at a packet level granularity. And that means it is very light on the, comparatively very light on the network, and providing the exact details that the analytics or a collector is expecting. So what kind of metadata do we capture? When did the packet arrive at the switch? When did the packet leave? That gives you how long the packet spent at each hop, right? Because per hop latency is a very important factor in identifying some use cases. And what port the packet arrived, what port the packet left, that gives you packet path tracking, right? Sometimes you want to understand whether the packet deviated from the usual pattern or not, right? So all these, and of course, there are other interesting details such as QID, if the queue congested or not, and all this metadata. Somebody was asking earlier, how long is the metadata or how big is the metadata? It takes 32 bytes. Per hop metadata is 32 bytes and is added. So if you have 5 hops, then 5 times 32 bytes is the metadata that goes to the collector. So this is a brand new technology and it is being adopted. Alibaba will talk about it, and there are several use cases to it, right? So we talked earlier about Rocky V2 optimization for AI, ML, and storage workloads. There are other use cases like application reachability detection, meaning proactively you monitor whether an application is reachable or not. And right, if a path is not good for reaching an application, they switch to an alternate path. So that is another use case. And you all know latency is a key problem that network operators have to deal with. And usually when an application complains about latency, it is the network that gets blamed unless proven otherwise. So what happens is, because we have per hop latency information, so whenever an application complains, then you can quickly see, okay, is it the network or the application that caused the problem? Because you have this per hop data, let us say it usually takes 200 microseconds to go through the network, and you are noticing around 200 microseconds, then you quickly rule out, okay, it is not the network that caused this additional latency. So you you focus on either application or something else. And this is a key issue, like where we encountered it with one customer who spent a lot of time troubleshooting network for an application problem, almost like days and all, right? And the other problem is a packet path tracking. So because we can identify how the packet exactly traversed what ports it went through, you will be, in data center, what happens is typically the packets take a fixed pattern. Even if you have ECMP, they get hashed into a particular member link, and they traverse through a predetermined or a particular pattern. And when a port went down or some transient condition occurs, that is when the packets deviate the usual pattern. And it is very important for customers. Like we have one customer in Taiwan who is using this use case with one of our OEM, the packet path tracking, meaning if the packets take, let's say, more than 6 hops, they want to be alerted by it, meaning something went wrong. So that's another use case. Congestion monitoring. Those of you who attended AI/ML related sessions, you all realize that AI/ML workloads are very different, and the network plays a very key role. And typically, Rocky RDMA and Rocky V2 is used for AI/ML workloads, which is very sensitive to latency or packet drops or queue buildup. And you can do congestion monitoring, regular congestion monitoring, or you can also utilize HPCC++ to act on it, right? One is like monitoring, the other is acting on it. So both use cases are supported by IFA. Another important thing is pro packets versus live traffic. So in the legacy silicon, we supported IFA for pro packets, and that enabled key use cases such as HPCC++. And but the thing is, supporting live traffic is possible, but you need to use it carefully, because if you enable IFA on a 10 Gbps flow, you can imagine the number of reports that are going to the collector. The collector will get bombarded, and you need to plan it carefully. So pro packets definitely solves many use cases, and those use cases where you need live traffic, that is also supported. The difference is live traffic means the user packet itself is used for adding the metadata in the data plane. Pro packets are something initiated specifically for monitoring purposes. And again, both are supported by the recent Broadcom silicon, such as Trident 4 or Jericho 2. And even though we have a IETF draft that we are working with Alibaba and other partners, we are also fully aligned and fully committed to bring that feature to the SAI community, and make sure it is part of this SAI specification, and the implementation is also supported, right? So we will be doing that going forward as well. With that, I will request my partner Ding to explain more details about their deployment use case. Thank you.
Hi, I'm Ding, and I'm working at a monitoring team at Alibaba Cloud. And now I'm going to talk about Alpha deployment at Alibaba. So a little bit about Alibaba Cloud. We founded in 2009, and we are #1 cloud computing company in China and Asia Pacific. And we serve more than 200 countries and regions. And this slide, the left view, the left part is the network architecture. It's very classic cloud network architecture. You have span, leaf, and server. And the right side is tracking history of my online shipping. You can see where is my package at a certain time and when it's be delivered. The message I want to deliver in this slide is user doesn't care about our network. Like online shopping, the customer doesn't care if you are using the FedEx or UPS, what kind of truck they are using. The only important thing for customer is she can track their package and get the history of the package. So back to the network, I think the users are same. They don't care about what kind of device you are using, what kind of architecture you are using, what kind of routing protocol you are using. So the only thing user care about is where is his packet, and when it be delivered, and is it lost or is it dropped or delayed at somewhere. So, but unfortunately, current the monitoring system we have, like gRPC, SMP, or syslog, cannot provide such information. They can tell if your device is wrong or CPU usage is high, but they cannot tell you what happened inside the network. So that's why we believe IFA can solve this issue, can provide such information to the user. So next, I'll talk about a little bit about the background. So we have a internal tool called Alipin. It's like a pin mesh. It's a network anomaly detection system. We deployed hundreds of thousands of Alipin agents in our networks, and they ping each other. So if your network, if network going down or some link goes down, we got signal from the Alipin. But there are some limitations. The first is they don't have path information. So I know something goes down, but I don't know where it is because our data center is ECMP. We don't know this flow, where is this flow. And another thing is it is unable to detect congestion. The last is it only measures end-to-end latency. That means if something goes slow, I don't know where the latency comes from. Is it come from the network or NIC or maybe Linux kernel? So that's all the limitation. So we think the IFA can solve all the limitations. So we start to integrate IFA with Alipin. So let's talk a little about the architecture and the mechanism behind the scene. So it's basically a ping process. One server ping another server. But you pay a close attention. So the right block, you can think of its original data, like a payload, like a IP information. The blue block is the IFA header. And the yellow block is the IFA metadata. It contains like an inbound, outbound interface, timestamp, and queue length, such information. So the switch append the metadata one by one if they see the IFA header. And at the end, we collect all the metadata and send to the local collector and shows to our NetOps team. So our NetOps team can know what happens in our network. So the next is let's talk about a little bit about scale. So we have 100,000 of Alipin agents in total. And each agent pings several dozen other agents. So basically, a single ping gonna generate one IFA message. So every cluster has tens of thousands of Aliping agents. And each class generates around 5 million alpha messages a day. That's a lot. And alpha reports are retained for 7 days. So that's a scale. So the challenges, the first thing is too many data. As I mentioned earlier, so it's basically every single ping gonna generate one alpha message. That means you double your monitoring traffic. It may be okay in your data center network because there is plenty of bandwidth, but you don't want your alpha traffic travel back and forth in your backbone. So the solution for that is terminate alpha traffic as early as possible. So what we did is we deploy a local collector in every single data center. So there is no alpha traffic in our backbone. And another problem is the computing resource, because we need to process such a large amount of data. And the computing resource, because we are a cloud computing company, so the computing resource is meant for used by user. So what we did is two way. One is batch upload, another is on-demand upload. So it means you can set some like a latency threshold. So we only report alpha message if the latency exceeds the threshold. So another challenge is network is heterogeneous. So that means you may have different vendor, different chip. So different chip may have slightly different alpha behavior. So some insert metadata at the beginning of your packet, and some append the metadata at the end of your packet. So we don't have too many choice for that. The only thing we did is adjust our software. After we collect all the metadata, we reorder of them and generate report to send to our ops team. So basically, that's all my topic, all my contents.
Yeah, thanks, Ding. Like Ding mentioned, right? There are few kind of things that can be done at the network level. When you have a heterogeneous network, basically you collect different pieces of information and you stitch them together so that you get the best out of the metadata that you are collecting. So Broadcom again tries to provide the best possible solution based on the network or based on the silicon that you are using, so that your use case is enabled at a higher level, right? Like whether it is latency monitoring or condition monitoring, etc. With that, again, this is a part of the Sonic specification. So please, you are welcome to join and contribute there. And as I mentioned, the IETF draft is also available, and you are welcome to contribute. Any questions?
Thank you. Any questions? Yeah, I have a question.
Yeah.
I know Bhaskar listed a bunch of metadata fields, but specifically in Aliping, what metadata fields are you using to detect the anomalies?
So we are using the path information, means the in-band interface, out-band interface. So we know which path this flow goes, the travel. And another thing is we use the latency, per hop latency. So if something goes slow, so I know which part of the network got congested. It's got more latency than others.
Do you need to time synchronization between those switches?
Yes.
How do you do that?
So basically we are one solution is used NTP, and another is another solution is we're using PTP, but it's another topic.
Yeah, that's a good point, actually. That's a good question, because you are measuring the telemetry at a hop by hop. We are talking about nanosecond level kind of things, and that's where Gohan asked, okay, hey, now how do you time synchronize, right? Or have you time synchronized? So if you really want to take advantage of this nanosecond level granularity of timestamps, etc., you need PTP based time synchronization, right? So PTP based time synchronization gives you much more higher granularity depending on the whether it is a transparent clock or a boundary clock. You get microsecond to nanosecond level granularity.
Ding, I have a question. So if you are only worried about latencies, then residence time is good enough. Why do you need time synchronization? And the report is generated by the end node.
Sorry, say again?
So if you are only worried about latency, then residence time is good enough, right?
Timestamp, you mean the good enough?
No, the residence.
Residence time, like meaning not like not necessarily which switch received first, but only okay, one particular hop received like 500 nanoseconds.
Yeah,
right?
yeah,
So
yeah. That's enough. That's enough.
So
We
my
don't care about like what time. We only care about the how long it takes for the switch to
process it, correct.
forward
Yeah.
the packet.
So my question is that if that's the case, why do you care about time synchronization?
Time synchronization. We don't care about time synchronization actually for this scenario.
Okay.
Yeah.
But you just said that you do care about time synchronization, PTP or NTP.
So it give you, for example, the PTP give you the more precise end-to-end latency. So if you are not using PTP, you are using timestamp from the kernel. So it's not pure physical
I got
latency.
I got it. Okay.
So yeah.
Okay. So just for a more accurate residence time, you want PTP or NTP, but not necessarily to synchronize the entire domain.
Yeah.
yeah, you're right. So if it is only residence time is of importance, then PTP is probably not required. But if you care relative time over the network, then PTP is required.
Got
Yeah,
it.
you're
Thank
right.
you.
Thank you. Sorry, we're out of time. I request you to take offline. So
Thank you all.